Okay, today we are looking at hypothesis testing and verification. I'll be using one of the libraries. It's a common library. Uh, it gives you the possibility to run different hypotheses. And so, we have stated it before. Basically, I think we're repeating it that a hypothesis, a hypothesis, before we even talk about a hypothesis, although we have explained the concept before, we said that when we were discussing concepts, we said we collect data from a sample because it would be very difficult for us to collect data from the entire population in most cases. If you are fortunate to collect data from the entire population, we call it a census. And out of a census, we have a sample, which is a subset of the population. Once you collect your data from the sample, it gives you possibility to perform some basic descriptive statistics. We could run measures of central tendency. We could measure measures of dispersion. And we could also look at maybe frequencies and percentages. We have to do with proportions and many others. It also gives you possibility to visualize your data using different charts, histograms, bar charts, pie charts, box plots, and many other types that you have. And so, all such analysis is classified under descriptive analysis. It's describing the state of that sample data you've collected. And so, what naturally happens is that we are not really very much interested in your sample. So statisticians or data scientists are not really they're not very interested in the sample in itself. They're only interested in the sample because this sample gives them the possibility, the ability to infer that what I've seen from the 1,000 short women that I interviewed who did whatsoever, if I interview the next 1,000, the next 5,000, they'll have the same behavior like the 1,000 that I collected. And so in such scenarios, we have what we call inferential statistics. Inferential because we want to infer from what we have seen from the descriptive statistics. Now, this comes because the descriptive statistics at times fail to tell us the size and the magnitude of what we are observing, or whether what we are observing is not by chance, or, or it is pointing to a real challenge within there, or is pointing to a realistic situation that deviates from our expectation. For instance, if you discover that, please don't be offended and don't take it to heart, it's just an example, that short women, if you're short, are generally what? Nagging. That was dealing with 1,000 women. Welcome. And so, and you collect data now and conclude that all short women are nagging. We'll call it an overstatement, right? Overgeneralization. You just deal with 1,000 women and you are saying that all short women are nagging. And so, what statistic does is that it says, okay, for us to see that what we have seen in this 1,000 women is not by chance, we need to verify a hypothesis. I can recall when we started, we basically talked about the case of John and his friends who were disturbing in class, right? Peter, Andrew, and the rest. And they gave them a punishment For them to carry water, they have to go to the stream and carry water every day. And they had to do that. The first day they carried, John carried, the second day, Henry, the third day, Andrew, fourth day, and Peter did not. And so when John carries, Peter, Henry, Andrew, and Stephen, they go and carry water for 4 days. They don't get angry with Peter. They may not really be happy that they've done it while Peter is there, but they believe that it's a fair game, and so whatever is happening is by chance. But if they have given them to carry water for 21 days, and after 10 days, Peter has never carried even once, they get to a point where they are like, hey, Peter, are you sure you're not cheating? Right? Because by standard expectation, the more they carry, the lower your chances of not going to the stream. 15 days, you have never gone to the stream when people have carried 3 times. We start becoming very worried. 18 days, we say you are cheating. You will not convince us that you're not cheating, right? No matter what you say, we have enough evidence to say that although we can't really say exactly what you are doing, but we know that you are manipulating the system. And so that conclusion now says that we have exhausted our let me say the liberty or the latitude to say that whatever is happening is by chance. Now we're in a stage where we are observing this as what? A fundamental cheating within the system. And so we can accept. In the same analogy, what happens in the court is basically somebody comes, accuses another person, you say, go and bring evidence, you bring evidence, they argue over and over and over. After that, the judge says, I've had enough evidence, and I can conclude that this person is either guilty or not guilty. It's only when the person has been presented what? You just say, I always do this, there's always that use of enough evidence, or that terminology, enough evidence, so that the decision you're trying to take is not based on what probability. It's still on probability, but you want to limit the fact that you will set somebody free who is supposed to be in prison. And at the same time, they also want to put somebody in prison who is supposed to be free. And so there's always that trade-off. So what this gives us in statistics is that it gives us now inferential statistics, and inferential statistics basically says, okay, after seeing all this evidence, let's try to see if the evidence we're having is not by chance, but pointing to what? A true underlying issue in our data set. And so once that is done, you can test hypothesis. Now, we said hypothesis is what? Basically what? An assumption, a proposition, a, a suggested answer to a question, research questions we have asked. And many times we say what? It is an educated answer to this. So we use hypotheses to draw conclusions about the population, although we did not collect data from the population. And I can also recall again that during our concepts, we mentioned this concept of what? The central limit theorem. What did we say was the central limit theorem? What did we say was the central limit theorem? What you are giving you. Now, before we talk about, we basically said the central limit theorem. To understand the central limit theorem, you need to understand the concept of normal distribution, right? A normal distribution means we have a significant proportion of our scores gathered around the center, which is around the mean. The further away you move from the center, the fewer the scores. That's why it gives us what we call a bell-shaped curve or the Gaussian distribution. Right? Now, that concept is very, very important. It translates to the idea of the central limit theorem. The central limit theorem says that in a large sample, or in a large population, if you sample or you pick up different samples with replacement or you are sampling out, the mean of each sample, right, will be approximately equal to the mean of the population, which we call the population parameter. Which means if we collect data, for instance, we talk about 100 women, right? The 100 short women that were nagging, and they had a mean of, let's say we measured in whatever, we have a mean of 70. So that means if the 100 women comes from that sample, if we collect another sample from that same population, their own mean will be approximately equal to what? To the mean of this 100 or 1000 that we have. If we take maybe 10 different samples, their means will look alike, right? All their indifferent means will at the same time resemble the population mean with a certain level of confidence. That's why we say we are testing at 95% confidence, because you are trying to establish that this mean that you have observed from here is highly likely to have come from this population with a mean of this. That's the idea. I don't know the population mean, but I can estimate with a certain degree of assurance that the mean will fall within this range of values. That's the concept. That these individual samples from that population have a mean, or their means are approximately equal. We're not saying that they're equal, but they're approximately equal, which means it may be a little bit higher, smaller, or but within a certain confines that we can predict with a degree of confidence. Please sit down. These concepts are important. We don't just take the concepts and we keep them. Yes. They are very vital. So we need to bring up a new rule. If you come to a client, they ask a question, don't answer. You stand up. Yes, I know it's tough, but attention, you need to force certain things, especially when it comes to adult learners. Adult learners don't learn like children. They are so distracted with so many things. So you need to force them to read. Right? So it is on the basis of that that we use sample to generalize about the population, because we know that this sample reflects the population. And it is on the basis of that we emphasize that you always try that your distribution should be what? Normally distributed. Otherwise, we use non-parametric tests, because they don't assume that distribution is normal. They don't assume that this sample or the mean we're getting comes from a known distribution. But the concept of the normal distribution still goes further to give us the fact that if our distribution is normal, then we will be able to estimate that 68% of our scores will fall between what? Plus or minus one standard deviation. All of these concepts are very important. Plus or minus one standard deviation, we said this. Then 95% of the score will fall between what? Plus or minus two standard deviation. That's what we said. Those are the concepts. So the 5% that falls out of that, we say that what is by chance. That the 5% is that we have enough evidence to agree or to suggest that what we're observing is coming not from, it's not occurring by chance, but there is an underlying reality. It's like we're saying that if we had up to 15 times of people going to the stream, we still think that's normal. But 19 times I have never gone once, we say no, we have exhausted the threshold of assuming that you are not cheating. You are cheating. After 19, we say no, whether you are cheating or not. The problem with hypothesis testing is that we have two types of errors, the type 1 error and the type 2 error. Those are concepts that we have discussed. Any question? Colleagues. So now when you collect your data and you want to analyze it, you always need to understand, emphasize this concept, know your research questions, know your hypothesis, or at least formulate. If nobody gives you a research question or hypothesis, it's good that you at least come up with some questions. It's good that you come up with objectives. You don't just analyze data in a space. You are guided. We can have two data sets or the same data set, but we'll come out with different conclusions and recommendations or different findings, depending on the questions we set about the data. And we said it also goes back to understanding the research problem you are trying to investigate, because all of that put together helps you to be able to analyze your data and come up with what? Authentic results. Now, we generally have two types of hypotheses. the null and the alternative, right? The null alternative is always looked upon as the state of affairs, right? Yes, it's like we can put it as it's always the normal reality. It is how situations are at the current state. For instance, we basically assume that what? We have two genders or yes, two genders. Let's use them two genders, male and female, right? That is the state of reality. But it gets to a time where we start seeing some what? New gender categories coming up. Those are what? Those are not normal situations. So the null hypothesis will be that we have two genders, right? But the alternative will be that what? We have different more than two genders. And so we can collect data now to prove whether the assumption we have more than two genders or we have two genders is true or they are true. Now what happens is that some people may say, okay, we are trying to define gender, only limiting it to what? Biological, but apart from biological, there are what? Social components that we should include. So with that, we have more than what? Two genders. It becomes an argument, right? We collect data and verify and draw conclusion. So that is the concept of how research works. Now, the alternative is a reverse. It basically says we have a difference. What we think that is not that like that. Right? I basically think that when you go to university and study accounting, you should come out and be an accountant. That's the standard. Right? But we can collect data and analyze and discover that not because it is accounting that you end up doing an accounting. Because there are people who did not do accounting in school that they are working as accountant. There are people who did accounting are working in different fields. So the notion that you are trained as an accountant, you must work as an accountant becomes what? It's not false. But what's the null hypothesis? That one, if you are trained as an accountant, you should work as an accountant. But is that true? It doesn't prevail like that in society because so many people have been trained as accountants and they're not working as accountants. But to what extent can we generalize that? Because you can come to Boya and collect sample, right? For 1,000 students and they've come out, and because Boya is too small, without so many companies, they have started their own businesses. Should we generalize that accountants, you study accounting, you must not work as accounting? It's difficult because we say that maybe the sample size that we are dealing with is too small. But if we collect a large sample size and we see it like that, then we can make it a general rule that even if you do accounting, you must not end up as an accountant and it becomes now a principle. It becomes like a general accepted something. So that's it. It was just to help us understand. Once you understand the concept of hypothesis, you need to now verify it. And so we basically, one of the things that I always say NGOs in particular do wrong is that they limit themselves a lot to descriptive statistics and they go ahead. Because when I met 10 women and they said this, and you come and you design a whole program based on their opinion. Now, quantitative studies don't believe in that. You get it? Yes. Remember, hypothesis testing is an aspect of quantitative studies. We may say propositions with qualitative, but you don't test it. But hypothesis test, the power of quantitative analysis is tied to what? Hypothesis testing. You are able to analyze your data from a sample and conclude that what you have seen in a sample will be applied to the population. And when we apply it, for instance, when this, if for those who have followed American elections, most of the time we depend on the polls. 68% of Americans support Trump, right? So we will project that will become the president. He ends up becoming the president. So what we are proposing based on our data ends up becoming what? Real. But the problem is if you go and say 68 and it was just about 200 people and you're saying 68%, which is not a representation, at the end of the day, will he become? He will not. Well, this high probability he will not because the sample was too small and did not cut across the entire country, did not take across most of the views. But if that generalization is coming from the entire country and cuts across most of the population and it reflects the voting population, then at the end of the day, the conclusion you take will be realistic. Because data, if it is well, will hardly lie. Although it's easier to lie with data. So, in other applications, we have different If you're using SPSS, we saw it, but in Python, we use two libraries to do that: Scipy and StatModels, statistical models, which basically used for hypothesis testing. And so you always have to import them so that you can be able to test your hypothesis with them. So that's the first thing we're taking. So we have to import, and again, just as an example, the null hypothesis, we say that what? It is an assumption you want to test. Now, many a times you hear they say we don't test the alternative hypothesis. We don't test the alternative hypothesis, we test the null hypothesis. Because we collect our data to either prove that what we already believe is or it is not, right? Yes. And what we say what we believe is basically the null. So we test the alternative hypothesis. I mean the null hypothesis, usually which is about the population. Then the alternative now investigate the opposite of the null. We basically say, for instance, we say the mean weight of apples is 500 is, then the alternative will be that it is different from that 500 kg. The average height of, let's say, students in lycée, boys, is 1.57, right? The alternative with that is what? Is different from 1.57. Now, this gives us two types of hypothesis testing, which we call the one-sided hypothesis or one-tailed test or two-tailed test. The one-tailed test says that with the one-tail, what happens is that you basically assume one direction. For instance, if we say that uh, the boys in lycée, right, the heights are below 1.6. So we have taken a direction, right? The direction is that everything will be less than or equal to, right? And so the alternative will be that it should be greater than 1.6. So it's directional because, or you say that if we increase the watering of a plant, the produce will increase. Then what? We're saying that what? We're taking directional because we're dealing with an increase. So we are certain that we have a positive and upward increase for the two items, or when one is increased, the other one. So it's directional. We will know the direction. But when we don't know the direction, we basically say there's an effect. Whether it will increase or decrease, we don't really know. So that's two-tail test. With one tail, you have a direction. With two tail, you don't have a direction. Now, when testing a hypothesis, what is important? You need to know at what level of hypothesis you are testing. Generally, traditionally, we have 95. You can test at 95%, right? 95 here gives us what we call the confidence level. The confidence level, how confident are you? And the confidence level gives us what we will help us to extrapolate or uh, let me use the word mimic the range of values to which the population mean will fall. For instance, if I test at 95% and I have the confidence level of the boys, let's get back to the case of we said the mean was for the boys in which school again, whether it was lycée or whatsoever, is 1.6, right? Let's assume it's 1.6. And I'm testing a 95% confidence level. And so I have a value of 1.5 and 1.7. Then I know that even if I have 95% confidence that the mean of the boys in lycée will be between 1.5 and the population mean. If I take from one, let's say I sample just 100 and test it and give me a value of 1.6, right? I know for my sample, I don't know for my population, which is the total number of boys in lycée. But if I have that confidence level, I know that I have 95% confidence or assurance that the mean will be between 1.5 and 1.7. That's the essence of confidence level. So you need to have a confidence level. And that confidence level gives us what we call the alpha, which is a significant value. Now, the case essence of significant value there, it helps you to know whether your results are not by chance So it gives us that alpha value of 0.05. That will always say if your value is less than 0.05, you can conclude. That's the concept. So it gives us that alpha value. So 95% gives us an alpha value of what? 0.05. While 10% gives us 95%, 90% confidence interval with an alpha value of what? 0.01. Then 99 gives us 0.001 in that order. So determine the p-value which the probability of a test statistic as extreme or more extreme than the one we observe. That is now what the concept of that, getting it by chance. That's the idea of the p-value. Now compare the p-value to significant level. We have said significant level maybe 0.05, which is the alpha value. So the one you get and you compare it with the one that was there. The significant level is usually denoted as alpha, is the maximum acceptability probability of rejecting the null hypothesis when it is true. It is what? The maximum acceptable probability. Now, what that basically means is whenever we are conducting, we are trying to establish a cutoff zone for which we can accept the null hypothesis or we reject the null hypothesis. Some people say we use the word accept or reject or we return. Those are kind of words. If the p-value is less than a significant level, you can reject the null hypothesis. We have already said this somewhere. The p-value is the one you have calculated. Then the significance is the one that we are testing at 95. So it gives us a significant value of what? 0.05. Now, many times when we are conducting a study, we want to either examine whether there's relationship or effect. So we do have what we call effect studies, or we have effect and relations go together where we have differences. Is there any difference between the average performance of boys and girls in a particular subject? That's a difference. We want to see whether two groups are different, right? We want to see whether teaching using a projector affects performance. Then that's an effect study. So teaching method using a projector affects performance. We can check that. So it's an effect study. Or we are trying to establish if teaching using a projector has any relationship with what? Performance. Now we mentioned again, we're doing that relationship or correlation establish relationship, not causation. So two things are related. Doesn't mean one is causing the other, right? That's the idea. So we have effects like relationship and we have differences. So most often your hypothesis, you are trying to establish whether there is an effect or there is a difference between the items. And so when we are looking for differences, we have most common statistical technique. We have mean compared, which we saw in SPSS, like what? The one sample t-test. We say the one sample t-test is very vital when you want to do kind of, if you're a mean officer, mean stands for, I think, what does it stand for again? Monitoring and evaluation, something like that, learning. Yeah. So if you are working in a company and there is a standard working, let's say performance, there is a rate that say, okay, for a student to, for a worker to receive bonuses, you must come to work 24 days a month. That's a standard. So 24 becomes a standard, right? Now, once that standard is established 24 days a month and somebody comes there, maybe 22 days or 23 or 21, should we still give the person a bonus or we should not? Right? Now, that only depends on what? How flexible are we to go out of the standard? So we can say, okay, if somebody comes 22 days, we still give the person the bonus, right? Or 26 days, wow, more extra bonus. But should we give somebody who attended work just for 20 days? Should we give for 15 days? So that information is vital. And so with one sample, you are able to have a standard and test against what? And evaluate now based on standard. The standard is the known mean, which is the 24 days. Every worker to receive bonus will work for 24 days. That is the mean, right? Now we can come and check. Daisy came to work. How many days did she come? 23 days. Should we give her? Should we consider that if you count 23 days, there is no significant difference as compared to 24? You get it? Yes. If there's significant difference, then they will not give you. But if your performance will not exhibit some significant difference, then they can still give you and say, okay, 23 we accept, 22 we accept, but 20 no, 15 You get that? So there is that expectation. So you can use the one sample t-test. Now, for the two sample t-test, you basically want to compare the mean of two groups. We talked about boys and girls in a class. For me, my experience was that most girls seem to be more intelligent than boys. I don't know whether that's true, right? I might be dealing with what? A sample size that is skewed. In most schools, the first three may be girls in each class, right? In that case, it says girls are more intelligent than we can assume, right? So in that case, we are having two groups, the groups of boys and the groups of girls. And so I verify if they have what? A significant difference in their performance. Significant difference means that difference is big enough for us to ignore. And I always use the case of athletics. The reason why we separate men and women from not participating in the same sport is because of what? Statistically, uh, there is statistical evidence that men and women don't have the same level of what? Performance or strength or whatsoever when it comes to sporting activities. But in a classroom exercise, we put men and women in the same class because there's no evidence that men are more intelligent or women are more intelligent than men. It is what? In is so gender will not play a role when it comes to what? A classroom scenario. So, but then what are we using? The independent sample t-test. So, in other words, an independent sample is a statistical technique that is used to examine or to test whether the mean of two unrelated groups is significantly different from each other. We are using the word mean, but we could also say the median if you are trying to deal with, but again, statistically we use the word mean because this is a parametric scenario. The independent sample t-test or the two sample t-test or the student t-test, those are various names again. The independent sample t-test, the sample t-test, and so on, or student t-test compares the means of two groups. We say two unrelated groups. That word unrelated is very important. Or two mutually exclusive. What that means is that if you are in group A, you cannot be in group B, right? Either you're a she or you're a he. So you belong to a single group and you belong to one group. You cannot be in a group and another group. No, that's how it works. So we use the independent. For the paired, we said, yes, it's also a statistical technique to compare two groups, but these groups must be related. So for intervention cases, related means a variable has, or a case, an observation have more than two observations. For instance, when you want to study academic performance, maybe they come before intervention, they check your performance, they come in the second semester, they take your first semester results, they compare with second semester results. It's the same person, but in two different settings, right? So we use what? Paired t-test. Now, these things we are saying may not make sense, may not be relevant. You might, why are we giving too much literature? But the truth is that the challenge I faced, she did some work and sent to me. I think I don't know where I asked her why did she choose to use independent sample t-test? Did I ask you, madam, why did you choose to use independent sample t-test in the work? Huh? You have not checked, but you use independent sample t-test. Why? What motivated you? It's, I'm not trying to condemn what you did, right? But what is the essence? To make us understand that we don't just use statistical techniques, we must know the context. Context is very important. Context comes in terms of what we say assumptions. So each of these things has assumptions, and you should always test the assumptions first. Verify the assumptions. For instance, for independent sample t-test, we say that one, we must have two variables, one continuous, one categorical. The categorical is a what? The one that has two categories, right? The independent is maybe is continuous. So we can be talking about academic performance measured maybe in terms of max scores, even on 100. So we can compare the means of this female population or female students and that of the male students and see whether they're significantly different. Now, again, we say significantly different because there's high probability they will be different. Two things must exhibit some differences, right? But we're not only interested in differences. We know that these differences will make a difference. Because if you put men and women in a class, there will be differences in their performance. But should we be worried? We will not be worried, right? But can we be worried when it comes to sporting activity? Yes. If we put that men and women should compete for the same exercise, no woman will ever win man come on rest of home. So by design, you have already caused the person to be eliminated from participating in that exercise. That's the idea that we're looking at. So ANOVA is an extension of the independent sample t-test. Basically an extension. Why the independent sample t-test or the two sample test handles the situation of two groups, ANOVA handles the situation of what? Two or more groups. In most cases, if it's two groups, you can use ANOVA, but it's recommended that you use what? The independent sample t-test or the two sample t-test. Then we have others. In case your data is not normally distributed, you are not expected to use this particular test that we have just mentioned. Yes, so these are tests that are used for what? Data that's normally distributed. So you must know how to test for normality. Then we have the other scenario, like if your data is categorical, then you can use what? Chi-square. Chi-square is one of the most common statistical techniques used for categorical variables to check for association. If two variables are associated. So if we're talking about performance, it was not measured in terms of what? Marks, maybe it was measured in terms of pass and fail, and we have male and female, then you will not use what? Independent sample t, you use what? You use the chi-square. Some people call it chi-square, whatever you call, but then, right? So it depends on the setting, the question you are trying to solve, how your data is measured. Some of these things are very vital. Please take them serious. Don't just analyze data. The difference between you, who says you are a data scientist, or a trained data scientist, is that you know when to use a statistical technique and to interpret the results accurately. Everybody can run the statistics. Whether you use a programming language, the emphasis is not the programming, the language you're using. But do you know when to use it? Can you interpret it? We use it correctly? Those are the important questions. You can cause a lot of harm in a company when you bring wrong analysis. It's when the company setting. In academics, you may play around because the result might not be applied in most cases. But not to say that you play with academic data. No, you still give the academic data same value and importance. But what I'm saying is it becomes more dangerous in the company setting. The company gives you data and you go and analyze the data wrongly and perform wrong statistical techniques and come and give conclusions that have nothing to do with what is happening. Nobody knows. You are the expert. That's why you are invited. That's why they recruited you to come and analyze the data. And you come and do wrong analysis. The company will depend on that resource. Make changes to your policies because you have informed them. Just for them to go and incur losses because you made mistakes. Your data was not clean. You used wrong statistical techniques. So when you see I'm talking and talking and talking, it seems as if I'm talking too much. But I want you to understand, or you guys to understand the importance of knowing when to use a statistical technique. Understand the concepts first and the application. Understand the concepts. I always emphasize on concepts, principles. Principles remain the same in any setting. Economics, accounting, banking, biology, health, whatever sector you want to think of, or whatever field. Because mean remains mean. The only difference that will be that the mean of what you're measuring. A businessman measures the average sales, right? In the hospital, they can measure what? The average temperature. It's the same concept. Differences in setting. But do you know what it means by average? Do you know what it means by the mean, the average, or the median, the mode? Do you know when to use it? And can you interpret your results accordingly? Questions. I've been singing a song and people are just listening. So, questions. I'm done singing. Yes, good question. What's the difference between t-test and z-test? What's the difference between t-test and z-test? Who knows what I mean by z-score? Yes, the lady who asked what's the difference between t-test and z-test?
So I don't know that they are a bit similar, but I don't know the name is different.
Don't know the.
That they are kind of similar, but they are not the same. I don't know the exact difference. That's what I'm asking.
Okay. One is used when the sample size is small, very small, less than 30. Another one is used when the sample size is greater than 30. So go and find out more on that. Obviously, the t-test is used for bigger samples. But again, I'll rarely say they're similar. Yes. Any question? Again. Do we have questions? So again, we start by importing our libraries. Then we import our data set. We have seen the Titanic data set. And so you can look at the one sample t-test. It's a one sample t-test technique used to determine whether the mean of a single sample is slightly different from expected. I've already explained the concept in details. What you need to understand, we have one sample data set that we want to test from a hypothesized mean or a known population mean. And so, what are some of the key assumptions for one sample? For one sample, before you use it, you need to check that you have the following, or these particular conditions are met. Your data is continuous. This we're talking about a dependent variable. If your data is not continuous, you cannot use one sample. Continuous data is because you want to calculate the mean, right? For instance, if we're talking about the current data set we have, we say the average mean, the continuous data there could be age. Age is measured in years. And so it must be a random. The sample should be randomly selected from the population. Yes, you don't need to use purposive or any different a sampling technique that doesn't give every participant equal chance. So that's why we go with the random. The data should be normally distributed. Again, we've said that for sample size, that's where she was asking the idea of maybe to use Z-score. Observations are independent. No, two observations are this, they're not coming from the same. So for the current data set we have, we can check some of those ideas before we make progress. First, we need to state our hypothesis. In this particular data set, we say that we assume that the passengers that were traveling in this ship had an average age of 40. So they are mainly adults with an average age of 40. That's assumption. Now, to verify this, we need to bring in our SciPy dot stats, and we take t stats 1 sample. So this is the statistical test that we have to import. So we go to Scipy, which is our library, import what? One sample. So but see how the keyword is written. And so we set our confidence level. So here we start by cleaning our data. Clean our data. You have an issue, but use your this now. What I'm explaining, where you have, you don't have it in your laptop. You have it in your laptop. Everything I'm saying is in your laptop. You mustn't look up there. You should focus on your screen. Forget about what is happening up there. You should be where I am now. Once under one sample t-test. Are you there? So we, we go down to the part that has to do with the code. Normally, you have to clean your data to ensure that there are no what missing. So the first line of code helps us to draw missing data, right? Then the second one now, we want to extract our variable age. So we say go into the data set that we have set this and extract the variable what? Age. Once we extract the variable age, we may do our descriptive statistics. For instance, maybe we say ages dot describe. You could give that age any name, right? You can look for the mean. That's all you want. You can look for standard deviation. We're able to do that with is, given what we have covered thus far. Once you have done that, you may want to print out a basic of the scores. Again, you say print number of observation. This we saw that you can just take the length of the data set, and so it will give us, which is count, 718 or 714 after we have dropped for missing data. So, what is the mean? The mean here comes from the descriptive statistics that we have done. The mean is 29 years. So we were saying that we should have an average age of what? 40, right? We started by anticipating that the average age here should be 40 years. But are we having 40? No. We even say about what? 29. Now we have 29 here. The question we want to ask ourselves, if this 29 is a problem, we can't say with certainty whether it's a problem or not, right? Although, looking at 40 and 29, the difference is quite high, right? The difference is quite high, but can we say that the ages are significantly different? We can only say that when we use the independent, the one sample t-test. Given that with descriptive statistics, we cannot generalize or we cannot say whether there is significant or not significant. That's the main thing why we cannot just say that because one is 40 and one is 29. Let's conclude now and say, okay, it is significant. No, that can be, but it's not significant. As well as different can be one and it's still very significant, or even less than one is significant, depending on what you are measuring. So we have our standard deviation, which is 40 years. Excuse me, please. Making us to understand that the average variation from the 40 years or from the mean is 14 years. The minimum, we have seen this, somebody was 4 months old, and the oldest was 80. And we have our first one start at 20, second one at 29, third one at 34 or 38. Now, just looking at it, we discovered that you bear with me that we may have outliers because if the third quarter ends at 38 and the maximum is at 40 or 80, then that difference is really high. But we need to verify with data. So we can make some progress now. We check the assumptions. So we can check one of the assumptions, just one. Shapiro. We are seeing Shapiro, right? We are doing SPSS. It's the same thing that we are applying. It's the same statistical technique. The difference is just the software. Shapiro is used to test, especially when the sample size is small. So, but here we have a sample size which is large. So Shapiro will obviously give us wrong results here because of its sensitivity nature. Nevertheless, we expect that with a large sample size, there's high probability that you observe a significant difference. So how do we test it? This is just define the statistics, stat, and its p-value. So we have the statistical value and the p-value. If it's normally displayed, we pass Shapiro. We write Shapiro and we pass our this thing. When we print the results, it will give us our Shapiro test. This is a Shapiro test, which is the stat that we have here. So this is like defining two variables on the same line of code. The statistical value and its p-value or probability value that we saw. So this is our probability value. Our probability value is 7 point this. Now, if you look keenly, you think that that's 7, but it's not 7. We get it? If you look at the end of that, you see that it's e to the minus 0.8. So this is a very small value. Yes, this value is less than 0.05, showing that the data is not normally distributed. So we we under normal circumstances should not use what? Shapiro. Or if you have to use Shapiro, you need to transform. Or we look for alternative tests and use. So, nevertheless, since we are doing for class exercise and practice, we can just move on. And so, again, this is just testing, first part testing for normality. The second part of the code here helps us to test for what? Our results. Then, what have we test? The one sample t-test. Now, to perform one sample t-test, you need to have this population mean, right? Or the hypothesized mean, the known population mean. So we did assume that the average age for people in that ship was 40. But what did we find? No, it was 29. So you need to bring in the hypothesis or the expectation. Then you now pass your test, which is one sample. And look at how the one sample is written, because you have to use it as such. Then you pass your variable ages and you pass your hypothesized population mean, which is population mean there as 40. So this would have been, we know that if we're writing the figures here, we put a 40 here, but since we need to write replacing, we put 40 here and we put age here, and they will analyze and give us results. Pardon, that was better, SPS. It's not better. It gives you the same thing. What's here? These are the two things. Don't look at this thing and it frightens you. If I remove this, if I remove all of this, you'll still have your results. This all the code that you have to do to perform for, to test for. This first part, if you import it, this is all what you need. The population mean and this line of code, nothing else. This all. So if I come here now, if I run this, uh, I just come and say, okay, you can now say print your population mean. We already know the population mean. Come and put your stat. Or if you put, maybe you have to put the t-test there. T-test, comma, p equals to, you bring, this is what you need to at least memorize or understand. This is the most important part of all of what we are doing there. So they say population not found. Means I did not run. Maybe this way I extracted it. So, so So if you want to print your t-stats, you just put your t-stats here. They'll give you the value, which is negative 19.00 this. That's because the sample mean is far less than the population mean. That's why the value is negative. So we have a mean difference, right? Now the difference with, yes, SPSS is easier and it's straightforward. It aligns with the way we use our application, but as a data scientist, you need to learn to use by this one because this one can easily be customized to anything or to any work. You get that? So once you run, you get your p-value. You just put your p-value, they'll print it. Print. You just put your p-value here. You can put your print. So we have our p-value and its probability, which is e to the minus is a very, it's not close to zero, but not zero. Showing that we have what? There's a significant difference between the ages of the sample age and what we expected. So if we put our age to be, let's change the value here. Our population mean here, not to be 40, but to be, where was the population? Where did we assume the population to be 40 again? We did define the population equals to 40 somewhere. Have you seen it? We did define the population. Okay, here. So we put our population to be 30, population mean. And we go back here. So we have defined our population. Where's my condom? One sample. Mhm. Even 30 is still significant margin. Let me see. Did I put 30? Mm. Let's write down. Here is 30. So you say this one is insignificant, right? Because this value is greater than 0.5. This is a t-value that we saw. This is a t-value here. So normally, this is what you take and you go and put on a table now and interpret. Interpret the mean. For instance, the mean of the sample was 29 years and we compared it against this. The mean difference is, you talk about the mean difference. And then you compare that significant or insignificant. That's all how you have to interpret that the results. In a similar vein, we can do independent sample t. Let's take a short break. Okay. We can continue.